Okay, you can hear me well? Awesome. All right, and I cannot hear you or see you on the other side, but I hope you guys are enjoying the meeting, and I'm sorry I couldn't be there in person. I had to go on travel, so I apologize for that, but I hope everyone is enjoying and learning and having a good time. Just to give a quick introduction about myself, my name is Amir Ibrahim, so I'm the PACE Atmospheric Correction lead. My focus within the PACE mission is to do atmospheric correction so we can get ocean color from the Ocean Color Instrument, OCI, which is a hyperspectral instrument. I think you have seen this probably several times already, but I just wanted to reiterate that PACE has three instruments. The Ocean Color instruments that spans the wavelengths from the UV to the infrared, and it's a hyperspectral. It has that goes from about 315 to 895 nanometer. And it samples every 2.5 nanometer, except in the fluorescence, it samples every 1.25 nanometer. It has dedicated, it has a bunch of multispectral shortwave infrared bands that goes from 940 to 2250. Some of these bands are dedicated to observe aerosols in clouds, but some of them are also designed and utilized for atmospheric correction. In particular, bands like 1038 nanometer, as well as 1250 and 2130. The polarimeters are very capable instruments that can be utilized for aerosol characterizations and cloud characterizations. But I'm not going to talk about this. Other colleagues will talk about this in future talks. This is basically a list of the required Ocean Color OCI products, particularly for Ocean Color. We're primarily interested, or what we want to, the goal is we want to get the water UV reflectance hyperspectrally within an uncertainty range that is useful for us to derive more interesting Ocean Color products, and Yvonne is going to talk about this next. Chlorophyll concentrations and fluorescence IOPs and other more advanced biogeochemical products. We have a requirement to produce these water UV reflectances within this baseline uncertainty, as you can see from this table, and they are kind of spectrally dependent. But the idea is that we are required to produce these products by doing atmospheric correction using OCI alone. We're not talking about utilizing polarimeters yet. We just want to be able to get these products just from OCI, atmospheric correction. And obviously, with more advancement of the multi-angle polarimeters, we will have the capability to even do better atmospheric correction in very complex atmospheric conditions. These uncertainties are primarily defined for open ocean, global deep ocean conditions. PACE is mentioned to monitor the global climate change, changing ocean biology on a global scale. So our primary interest is to look at the climate signals and produce climate quality data sets. So we're focused on open ocean, but obviously we are really interested in coastal waters, and we want to be able to do amazing stuff in coast, because it's a lot more interesting than just looking at the open ocean. So the atmospheric correction problem, basically we measure from the PACE satellite with a hyperspectral radiometer the top of the atmosphere radiance, or what we call LT here, which is spectrally dependent. And we basically kind of simplify or say that the probably atmosphere signal is basically a summation of different radiometric contributions of different contributors to that signal of the atmosphere. That could be the molecular scattering or Rayleigh scattering, aerosols. There are aerosol particles in the atmosphere that absorb and scatter Obviously, the surface glint and the white caps, as well as what we're really interested in is water leaving reflectance. All of the signals modulated by the absorbing gases in the atmosphere. So so basically this equation here kind of like define like what these sort of contributions are, and we sum them up, and what we want to derive is the water leaving reflectance. So it's really important for us to model and predict very well the Rayleigh scattering contribution, the aerosol contribution, glint, and white caps. It's relatively easy for us to model the Rayleigh scattering. Is very well predicted, very well modeled. If we know our geometry and wind speed, we can predict the white caps and the glint. The challenging aspect of the atmospheric correction is actually the aerosol contribution. We really want to, the aerosol signal or the aerosol in the atmosphere changes spatially and temporally. So it's really important for us to quantify the aerosol concentration and what kind of aerosol do we have in the atmosphere in order to do the atmospheric correction properly. But also going into the hyperspectral era, we want to get a continuous spectrum of the luminescence and reflectance, so we can derive our amazing ocean color products. So it's really important for us to do also a good compensation of absorbing gases, which is basically these absorbing gases include contribution from water vapor, ozone, NO2, and oxygen. So if we don't do correction for these absorbing gases, we get a lot of neutrons and bumps in the reflectance, and we can attribute that to changing biology, which is not necessarily, which is not true. So it's really important for us to do a proper gas correction there compared to multispectral heritage sensors that typically avoid these absorbing bands. So this is the same equation as before. So the way we do the atmospheric correction is we use CDAS to do that. CDAS basically is the software package visualization tool that is behind it, is the software that does the processing from basically level 0 products from row counts measured by the sensor all the way to level 3 and 4 products. And this software is called L2Gen. L2Gen basically is the part of the software that does the processing from level 1 to level 2. There are other parts of the code that does the level 0 to level 1 and level 2 to level 3 and 4. So I'll focus on L2Gen aspect, which is basically take the top of the atmosphere, calibrated and geolocated and navigated top of the atmosphere reflectances to the level 2 product. For us is the luminescence reflectance. So the way we do this is that we basically create a sensor-specific lookup tables, for Rayleigh atmosphere. Like I said, we can predict Rayleigh very well, so we have sensor-specific lookup tables to do the correction. And we have also sensor-specific lookup table for the aerosols, as well as things like white caps and glint. All of this information are utilized together in an algorithm to remove the atmospheric contribution so we can get to the surface reflectance. So the NASA, over the past several decades, we're focused on developing an operational algorithm. By operational, I mean that an algorithm that is capable of processing level 2 products within a reasonable amount of time and produce that on a global scale. So the heritage approach is back from the C-Web's era's Gordon Wang approach, which is basically, by here I'm talking about the aerosol correction, so I'm focusing on the aerosol correction right now, because this is the most difficult part in the atmospheric correction. the Gordon-Wang approach, which is basically uses a single scattering approximation and then has some kind of polynomial fits that goes to the multiple scattering. Back in 2010, Ahmed et al. He did work on basically taking the Gordon-Wang approach to do multiple scattering calculation in a more sophisticated version of Fourier transfer. And both of these approaches, Gordon-Wang and the Ahmed 2010, or what we call the multi-scattering epsilon or MSEPS algorithm, basically relies on two bands and a near infrared to infer the information about the aerosol. So as we know that the further we go into the longer wavelengths into near infrared and shortwave infrared, the water absorption is so significant that the ocean is basically dark when you look at it at the surface level. So if you look at the top of the atmosphere signal, whatever contribution you're looking at from the satellite is primarily coming from the atmosphere and surface glint. So if we know how to model the surface glint, if we know how to model the Rayleigh contribution and remove that contribution, where basically whatever is left there is primarily coming from the aerosol signal. So the Gordon-Wang and the MSEPS approach basically use two bands in the near infrared to infer information about the aerosol concentration and the aerosol to get the aerosol signal and remove the aerosol signal from the top of the atmosphere to get to the water lumen reflectance. In 2019, we published a paper on using rather than using two bands to do the aerosol correction, we used multiple bands, or that was multi-band AC, multi-band atmospheric correction. So going into the hyperspectral era, now what if we want to utilize more spectral bands? Now we have all these bands available to us, so we have the ability, rather than just relying on two bands to infer the aerosol, we can now fit our top of the atmosphere signal was an aerosol tables or models basically to predict the concentration and the type of the aerosols to do the correction by using multiple bands in the near infrared, and we can go further into the shortwave infrared. And the advantages for the shortwave infrared is the further you go into the shortwave infrared, the more water absorption you get, which is really beneficial when you look at extremely turbid water conditions where our assumption about this, what we call black pixel assumption, breaks down basically when you have very turbid water conditions. When you open the ocean, where you have low scattering particles and low concentration particles, the black pixel assumption works fine. But the further you go into the coastal, more complex water conditions, this assumption kind of breaks down. So you need to either utilize a model to model the near infrared signal of the ocean, or go further into shortwave infrared. So the way that the multi-band EC works is that basically we take, as I said before, take our top of the atmosphere signal. We know well how to model the Rayleigh, the gas, the glint. We remove all these contributions, and whatever is left is basically is the aerosol signal. And using this aerosol signal, we basically have the ability to predict its concentration through the aerosol through depth. And then the next step is, okay, we want to know what kind of aerosol do we have in the atmosphere, because the size distribution and refractivity of these particles have different spectral shape and spectral response, so we want to be able to infer that information from the data as well. And this is where it comes, the multi-band aspect, where we do a chi-square minimization to basically infer the information about the aerosol model. And then once we find the best models that fits our signal, we basically remove the aerosol contribution. Then whatever signal we have is water lumen reflectance. And I just want to emphasize that we use something called spectral weight in our algorithm fitting. It's basically something where we it's basically something that allows us to tune the algorithm at which band we want to do the atmospheric correction. So when we know that we have very clear water conditions, we basically utilize we utilize all the band equally. The near-infrared band, shortwave infrared bands normalized, but their measurement uncertainty. So the measurement uncertainty basically plays a factor in it. But if you go into very coastal waters, where we know that the near-infrared bands are contaminated by the bright water conditions, then we start to shift that weight toward longer wavelengths, where we say, okay, we want to now rely more on the shortwave infrared to do better separation in coastal waters. And basically, this is an example, like data from OLGI at like 1020 nanometer, where you would, at 1020 you would expect, okay, in the open ocean conditions, it's going to be very dark signal, but in fact, if you look at very coastal estuaries, you see that even at the 1020 nanometer shortwave infrared, the signal is still high, and you need to go further into the endosphere in order to separate the ocean from the atmosphere. This is basically summarizing what I was talking about before, is that the multi-band AC algorithm is used for PACE, but it can be used for other heritage sensor modes, VIIRS, as well as feature sensors such as Glimmer. And this algorithm implementation would allow us to have the ability to utilize the near-infrared bands and the short-wave infrared bands whenever they are available. Just wanted to emphasize one particular aspect that we faced with the PACE mission is the computational efficiency and the data storage. So when you guys run CDAS during the training, and you process level 1 to level 2 images, if you try to use like multispectral sensor like MODIS or VIIRS, you can see the processing is very quick and efficient. But going into the hyperspectral era, now we have hundreds of additional bands that basically blows up the dimensions of these lookup tables that I was talking about before for the aerosols and other components. So it is the computational efficiency for hyperspectral sensors is becoming a lot more challenging. So as you can see in this example, so this is the dimension of our aerosol lookup table. So it has basically about 7.8 billion data points in it, and doing loading this lookup table into the memory, to the CDAS, and moving the processing is very very challenging. So the way that we want to resolve this problem is we want to utilize more sophisticated approaches to deal with this explosion of dimension issues. So again, this slide basically kind of show you how the lookup table looks like. So imagine you have like a lookup table that has the spectral dimension on one axis and all of the additional information on the other axis, like the aerosol type, geometries, and so on. So this is how kind of you parameterize your lookup table. And what we found is that when you model the aerosol reflectance of the atmosphere, the correlation from band to band is very high. So this kind of correlation matrix shows that this scatter plot also shows that the correlation in the aerosol reflectance from 560, for example, to 565 is very high, which tells you that this signal at the top of the atmosphere is very smooth. So how can we utilize that information to further reduce this dimensional lookup table? So what we ended up doing is try to use compression techniques to reduce the size of the lookup table so we can speed up the computational efficiency of our processing. So we run CDAS, you run within reasonable time. So we ended up utilizing principal component analysis, which is a form of simple machine learning technique. And it's basically, the idea is basically rather than storing our information as a function of wavelengths, we want to reduce that spectral information to principal components, so the components that really matters. And you use this principal components, you have to choose a number of principal components, and you basically adjust the number of principal components to try to minimize the number of principal components so that your uncertainty is below your measurement uncertainty. So if we ended up choosing 30 principal components, you're basically, you end up significantly reducing the size of your lookup tables, you end up significantly improve the computational efficiency in your processing without compromising or adding additional uncertainty. So you can see the figure below here, this is the percent error in reflectance, and it's very, very negligible. So I just want to show you, this is some data from PACE OTI using this MDAC approach with the principal component approach. And this is atomic atmosphere measurements. And basically you can see that the this is first light images that actually some of my colleagues shared before. The minute that we were able to get the PACE OCI data, we were able to process the level 2 products and get luminescence reflectance and chlorophyll products. And without doing this computational efficiency improvement approach using PCA, processing an image like that would take 4 hours or so. But if you have the ability to, if you utilize this PCA approach, you basically can reduce computational time to about 40 minutes. So that was a significant improvement to us, and that allows us to do processing more large scale. This is also a first light image that shows the comparison between the chlorophyll concentration between PACE and OCI. So although we did a lot of effort to try to simulate PACE data and then make sure that that before launch these approaches are working and functioning, we utilize PyTorch simulation, and I think I'll talk about that. We were very happy that when we got the first light images and we were able to process using these new techniques, we were able to get very, very good agreement between the PACE data from first light images basically to heritage sensor that is processed using a traditional approach, such as Beers data. In fact, what we noticed is that PACE also did have a lot less spatial artifacts and more accurate representation in the chlorophyll field. And there are a few reasons to that. Is that OCI has the ability to tilt, so it avoids a lot of the sampling that Beers, for example, cannot do. So Beers cannot avoid the glint. So when we do the atmospheric correction in the glint, it's a lot more challenging. So you end up seeing a lot of spatial artifacts and open products that PACE OCI does not see. Also, there are other spatial artifacts related to calibration, and PACE calibration was really, really amazing from first light images. This is a spectral comparison in the luminescence reflectance between OCI and Beers. So again, this is version 1 processing. So the first images that we got, if we compare OCI to Beers, we found a really, really good agreement, which is fantastic. It indicates that the instrument is very well calibrated. Also indicates that our algorithms processing from level 1 to level 2 is also functioning and working very well, at least similar to the heritage methods, if not better. But what we did notice is that there are a lot of spectral artifacts in the version 1 processing. So we're not sure, are these artifacts related to the algorithms, is it the gases or anything like that? Some of it, yes, were attributed to gases. We did update our gas correction method to improve things a little bit, but a lot of these artifacts were primarily coming from calibration because we were so early in the mission, the calibration haven't been updated yet. So when we did update our calibration and we were processing.
One more minute, sorry, the transition.
Yeah. We basically were able to show a significant improvement in the spectral reflectance, and a lot of these spectral artifacts kind of disappeared, which made us very happy. So whatever version 2 you have, it's a lot more useful and interesting to look at. This is the last slide. I wanted to tell you that there are so many challenges and opportunities with the PACE mission. The challenges that we're facing right now is UV is new to us. We want to be able to utilize UV better. We want to be able to improve the atmospheric correction in very complex water conditions and atmospheric conditions. But with that comes opportunities because of the great UV measurements that OCI will provide. We have a better ability to retrieve better information about the atmosphere, better information about the aerosols, and we have great sweep performance. And in the future, we're going to work toward the synergy between the ocean color instrument and their multi-angle parameters to improve the atmosphere. So I know it took a lot of time, so this is it. That's it. Those are the the slides that I have. So if I have time for questions, feel free to ask. If not, feel free to email me anytime. Can provide email, or Anna can provide my email to you.